Alright, new dawn, new day. Finally was able to get enough sleep to wake up and go to the gym in the morning, so feeling awake, feeling pretty good. Time to do another day of Microsoft prep. I think the goal today is not necessarily to do binary search, just not going to keep that in the title for now. The goal is to do a session on binary search as a warm-up for Microsoft, hopefully finish it relatively fast, and then afterwards go through LeetCode and do some of the bigger Microsoft tagged questions. Because I found that, at least for Google, it did help me a little bit because I was able to review trees a lot more than I would have normally. But I hope that it's the same for Microsoft here. Gotta check my email real quick. I gotta figure out, I got an advising appointment today. Just gotta figure out when that advising appointment is. 12 p.m. Perfect, okay. So I do have time today. Okay, let's go ahead and get started. Let's see what we got. Longest common prefix. Given a lowercase alphabet string words, return the longest common prefix. Okay, so a couple things to note right off the bat. This should not be in Python, that's for sure. Are all of these in Python now? They're not. Okay. What is this? Kth smallest element. Given an unsorted integer nums, return the kth zero indexed smallest element of the list. This one I can just tackle right off the bat. We are going to do a priority queue. We're going to add the elements to it. And we are going to pull k elements and return that element. Because I think adding to a priority queue is based off of a BST, which is what log n time average to add, which is okay. Let's go ahead and do that. Priority queue of integer equals new Q4 is the easy one. So, crap, how do I instantiate a priority queue? I forgot. I haven't used priority queues in a while. It's like, is it just a priority queue or is this more, there more to it? Yeah, okay. So it is just priority queue. I couldn't remember if priority queue was an actual class or if it was like a wrapper sort of like list or queue was. Int I in nums. Let's actually name this pq. pq.add. pq.add I. It utilizes a very specific data struct. Because I want to check real quick. Priority queue add time complexity. This should be log n, perfect. And then O of n average time. Add is log n. Then we're gonna do for int while k greater than 0. We're gonna do pq.pull and k minus minus, and then we're gonna return k.pull. Let's see topics. I think you might have to do it. Let's see. So there are k minus 1 smaller elements. You can use heap of 5, you can create heap and O of n. It's recursive. Divide and conquer. Hate it. We're gonna not do that. Okay, merging k sorted list. Given a list of sorted integers, merge them into one large sorted list. This is not gonna be too terribly difficult. I'm gonna do an easy than bounce, I bet. So, how can we then, let's do this, right? We're gonna make a list of integer, array list equals new array list. What we need to do is do this, keep track of int cur_min equals integer.min value int cur_min index equals 0. Okay. The thing is, this is a two-dimensional array. Merge case sorted, my favorite. How's it going? Yeah, the fact that it's an array makes it a little difficult to do because you can't exactly just remove things from the array. I guess the other way that I would think about approaching this is to, because we do need to keep track of which index we are at in which array, which means that we need, what do we need? I'd say maybe like a, hashmap seems too big for this. We can just do int indices equals new int of size lists dot length. This will allow us to keep track of which index we are at in each array. So what we need to do is, but how do we tell when we're done? I guess we can keep maybe a boolean for now. Boolean found min false. Then we can say for I guess we have to, we run until we can no longer find an element. Let's do boolean done equals false while not done. So here what we need to do is do an iteration through all of our lists. Oh wow, the sun just like blipped in and out of a cloud for a second there. That's kind of cool. Okay, so for int I equals 0, I is less than lists dot length I plus plus. Cool. We need to check, first of all, if indices where at, I don't want to spell indices every time. So if where at I is greater than or equal to lists at I dot length, okay, this needs to be a not. So this needs to be less than or equal to. So pretty much saying, checking first, are there more elements here? Then you can say and lists at I at indices at where at I is greater than less than cur_min, then we know we found a new min. We can go ahead and update this. So we can say that cur_min equals lists at I at index where at currently at I. And then we can say cur there we go. Kerman index is going to be equal to I, because we're grabbing from the ith list, and we're going to then update. We're not going to update just yet. After the loop, need to add to list and shift index by 1. So we're going to say list.add. We're going to add, what are we going to add? We're going to add Kerman to this, and then we're going to say lists at, not list at I, it's going to be where at Kerman index plus plus. So we're going to increment move pointer we currently look at by 1. And then say okay, bye. See ya. Okay. So what we need to do here is to say also found min equals true. And here at the end of all this, if found min found min equals false, and we just continue to loop through this. Else, if we did not find the min, meaning everything that we've looked through has already been taken care of, done equals true, then you must be hacking. Wait, number 4? It's not that bad to do. Beat me to it. Okay, done equals true, and first of all, let's do return. Let's do int result equals new int of size, let's say 10 for now. We're going to do system.out.println list.toString to see what our list looks like before actually converting it. Actually, I might as well just convert this here. List.size. Laziness is getting to me with this. List.size. Result at I. I really don't like the fact that you have to do this sort of overhead every time. Like every time you work with a list and then have to... Would it be faster to find the max k times? I mean, you'd have to store that also. So my general idea, here, let me return result. If this was working with lists, this would be very easy, but because it's, let me just fix the compilation error. Where is it? Line 6. Where at lists dot length. So my general idea here is to index 0 out of bounds for 0, line 14. I basically just iterate through. I keep pointers to where we are in each array, and I find, based on those pointers, find the minimum through the iteration, add it to the list, and increment that pointer by 1. And then that way, let's say the minimum here would be 3 that I keep. I would increment, so this would be pointing here, and the rest would still be pointing to the beginning. And I do that over and over until I end up adding all the elements to the list. Really, line 14, but... index 0 out of bounds for 0. I guess if lists at I dot length is greater than or equal to greater than 0, sure. Not 9, 0. Okay, this should take care of that. Wrong answer. Ah, okay. Oh, right. This needs to be max. N times k, where n is total elements. I think it should be, because it is gonna end up being, if assuming k is a constant, it is just gonna be O of n time, I think. Actually, no. No, it's not O of n time. It's actually, because it runs once, and each time it runs, it adds it adds another element. That's a good question. I'd have to put more thought into what the time complexity for this thing is. Okay, well, we got 2 zeros somehow, so. Wonder why. Because it's never going to be less. So we're gonna move this declaration from here to here. Okay, gotta see this great. I want to see your approach to this as well. So this is going to be min trackers. Runtime error, index out of bounds, line 16. Really? So moving this in here somehow gives a runtime error. Why is that a runtime error, though, is my question. Okay, let's do it. Let's do it. Okay. So why is this a runtime error? Permanent. Okay, list dot length 16. I don't even know what we're looking at. Okay. Hey, thanks, man. Appreciate it. Let's print this out. Println I guess. Let's see how far we're getting in this loop. Yeah, good luck, man. Take care. Okay, so if list dot length. Right here. I think that's that. Yep, that fixes it. Cool. It was an equal sign that was giving an index out of bounds exception there. Hey, okay, so look, yeah, that works. It's just, so we just need to move this into here. There we go. Indent this properly. Run. Boom. Submit. Slow. Way too slow. Way too slow. How do I make this faster then? Because it's a working solution, it's just kind of slow. What is a faster... I guess a faster approach that I can think of would be to just use like a priority queue. Alright, let's try a different approach here. I'm gonna do this, right? Int I equals 0, I is less than. We're gonna get rid of all of this overhead and try and bump this down a lot. I is less than what? Lists dot length plus plus. Let's make another priority queue. Q. Is that how you do it? Okay, priority queue. PQ is equal to new priority queue. Gonna just add them to an implicitly sorted collection. Length int j equals 0, j less than lists at I dot length. Cool. We're gonna make sure to increment the correct variable here. There we go. Don't even need this list anymore. I'm gonna do pq.add lists I j. There we go. Result is new pq.size pq.poll. Should do the same thing. Less than result.length. I might have like overthought this problem a little bit. So does not compile, huh? Priority. How do you spell priority queue? U-E 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 Priority queue. Goodness. Okay. Please just be fast enough. Hey, okay. Let's see. Divide and conquer, heap, and array. Want to follow up? Yeah, go for it. What's the follow-up question here? I want to look at what the easy ones are. Given us a string ops where do it in OK space. O and K extra space is because yeah, this is an O of N space. Let me tackle these other two questions, and then if I have time, I'll come back to this one and try and do it in O of K space. For int I equals string for int string s in ops. Let's make a stack as well of strings. So O of K space implies we keep one value per note per list, right? If I'm understanding that correctly. Didn't take advantage of the fact that each list was sorted just as a hint. I guess maybe we can, the way I'd assume to do it is, I'll just write out kind of a basic in the comments here. You make an array where you store the min, like the first element in the list, you find min of those k elements, add it, grab the next one from that list. I'd assume this would be the solution to it, because this is doing it in, yeah. The thing is, that's kind of what my first solution was doing. If you look at the one that TLE'd, I would iterate through the list. I wouldn't be explicitly storing it, because this is doing it, not counting the list here, because I mean this is just a solution thing, I wouldn't count that. It is doing it technically in O of k space. It's doing sort of that, but it is slower, I think. Because I am just like resorting them here. Okay. If there are any invalid operations, okay. If s dot equals pop, we do that. This should not be in here. Yeah, I'm just not sure how to make that particularly faster per se. Else if s dot equals duplicate. There you go. Let's just copy this else elif statement. It's going to return -1 because if any of that would be invalid, that's going to be a plus. This one's going to be a minus. I'm going to take a few seconds for a break here, step out, and then be back to solve this. Okay, so we got all of our checks in place. Now it's just a matter of, so first things for pop, if stack is empty. If we have no elements, return. It's kind of interesting because, why should your keyboard you're handsome? I don't know, I feel like it makes it a bit kind of prettier to look at here. The interesting thing is, my last Google question, it was a fairly simple question in its own right, but what the main focus of the question was edge case handling. So that, I think that this questions like this, sometimes where you're supposed to check for all the edge cases, make it, you know, it's a decent thing to prep for as well, because okay, so if it's empty, do that. Otherwise, stack.pop. Cool, that one's easy. Duplicate means duplicate the top element. So again, if stack.is empty, we return -1 because it's an invalid operation. Int temp equals stack.pop. Stack.push temp And we copy this and we just do it twice. Then for the plus, we need to make sure the if stack.size is less than 2, 0, 1, 2, yeah, less than 2 elements, then we can go ahead and return -1. Else, otherwise, int 1 equals stack.pop. Int 2 equals stack.pop. Stack.push 1 plus 2. Cool, and then I think we can do something very similar for this. I'm not sure if we get a concurrent modification issue if we do stack.push, stack.pop plus stack.pop. So I'm just going to do it this way. Top minus bottom. After this for loop, we return stack if stack.size stack is empty. Let's do that. Return stack.pop. Cool. And we're going to do that, and that should just be good. F stack.size. Where is that? Line 21. There it is. Didn't copy it correctly. Yeah, string is a single data type. Alright, stack.pop. Oh, I forgot these are string. Wait. I'm dumb. A little bit dumb. Wait, hold on. Oh, a non-negative integer should be pushed onto the stack. I am kind of a little bit dumb. Okay. Make that an else. I missed that first conditional entirely because it didn't have like the little bubble thing by it. If s dot is digit, I think it was, stack dot push integer dot parseInt s. There you go. I'm gonna check real quick. Java check if string is integer. I believe there's just a method. It might be a JS method that I'm thinking of, but let's see. There has to be a method for this. What if, okay, get this, right? What if we just write like a try-catch block? Wait a minute. No. I know what to do. So here's what we're going to do. Assuming all of our actual arguments are valid, if it's none of those, it's going to be an integer. So we're going to do stack.push integer.parseInt s. Easy. And the stack needs to be a stack of integers. There you go. Boom. Problem solved. Why is it so slow? Okay, I guess it's fast. Gotta love binary search times. Cool. Back to like this first question. Longest common prefix. A couple things I think to note about this one right away. The longest common prefix cannot be longer than the shortest word. What else? Longest common prefix cannot be longer than the shortest word. is just a for loop that iterates through. So let's do a string prefix equals an empty string. And we can, let's do this, right? Raised out sort words. For int I equals 0, I less than. Let's get this in a while loop. So like, while not found. And we're gonna make not found true. Actually, we're gonna name it found, I think is better. What does sorting do? Just it's kind of a lame way to just find the shortest word. I just can't be asked to, actually, you know, no, I'll find the shortest word. Because it has to be a common prefix between all of them. Found equals false. Cool. Let's do this. String shortest equals words 0 for int I. Let's do string, just, we don't really need to s in words. If s dot length right, because like it sorts lexicographically, not by length, and I'd have to write my own comparator to do it the other way. Always forget that strings sort lexicographically. S dot length is less than shortest. Shortest equals s. This will just allow us to do our comparison, and we don't want to run longer than this shortest string here. While not found. Prefix. Let's keep a pointer into shortest. Equals 0. We're gonna do prefix equals prefix plus shortest at I. And the cop out, I know you could do this by just like iterating through the first however prefix elements, making sure they're the same and everything. But I think Java strings have a starts with method. So I think we can just utilize that here because it is a built-in method. S starts with, there we go. So what we're gonna do is to say shortest at I for string s in words, if not s dot starts with prefix. Let's do this. How do I do this? Because we need to, okay, let's start with prefix, found equals true, and here we're going to just return prefix. However, the issue with this is going to be prefix.substring of prefix of 0 to prefix.length. Because we need to cut that last character out. I think that should do it, honestly. Should be... shortest.char@. Again, JS. It's very difficult to just hop languages. Char@ pointer. Very sloppy, this solution. Gonna increment pointer. Make sure that we don't okay, I probably need to weird, okay. Because they should all start with that. How does this method work? String prefix. Test if the string starts with a specified prefix. Yeah, it should. Oh, well, okay, well, we don't want to print out the string prefix here. There you go. Weird. Oh, right. Right. Mm-hmm. While not found, and pointer less than shortest dot length. Make sure we actually keep this. Okay. Okay, yep, this is where the issue we run into happens. Because we should be returning an empty string, but we are not. Okay, so dang it. Is this really going to be the question that gets me here? Okay. What if we do the prefix addition after? My result was AN. So I think the prefix addition does need to happen beforehand. Weird, okay. I can't seem to kind of, for some reason, visualize this in my head. So our prefix here is just going to be A. Wait, if it doesn't start with it, right, why can't we just return prefix dot substring 0 to prefix dot length -1, because it's exclusive. Should fix the problem. Yeah, there you go. Easy. Forgot that it's exclusive, but it's also 0 indexed. Still terribly slow, but go on. I'm waiting. Test cases suck. Oh my goodness, dude, this is... Why is this so slow? I think, honestly, it is, it's this search right here that's slow, I think. Iterate one letter at a time for each word and check they must all be equal. Move up until we can't. Think about the shortest word and the longest word, yeah. I think that would still work, right? Because here, let's try it, right? Let's try this. Because we can edit them ourselves. Yep, there you go. My result was expected. So yeah, it does work. Yeah, so let's go ahead and I guess go through and figure out the time and space complexities of all of these solutions, and then I think, honestly, I'm probably going to be done for the day. Didn't sleep all too much, so I don't know how much more of this I have in me. So, this one's going to run in O of n, and this one runs in... I think this is an n squared, actually. Because at worst, our length is going to be the... If they're all the same length, it's going to be n. And this check is going to run, I guess, like n times n, or like n times a constant somewhere there. Space complexity is just O of 1 because we're only utilizing like variables and strings. Word machine runs in O of n time with O of n space for this stack for all the elements that we're giving it. Merging case sorted lists, it runs in O of n space because of the priority queue. We have to add all the elements to it. And let's look up priority queue add. Priority queue add method, I need the time complexity for it. I think this is going to be n, it's just going to be log n to add, yeah. So for this part right here, this is going to be n log n, because we're iterating through every element through n elements, and it's going to take us log n per each element. So it's going to be, I believe, n log n for that part. Polling from a, I believe is, poll is log n. So it's log n both ways, so it's just an n log n, I believe. Time complexity with a n space. This one, again, I didn't do, I don't think the way that they were intending me to do it, but anytime I see k and like find the kth anything, my mind instantly jumps to using a priority queue, because it's implicitly sorted, and because it's based on binary search trees, it is, it's quite fast at implicitly sorting. Sorting a list generally and then iterating to the kth element would be n log n for the sort at most, while I think this actually, no, this still ends up being n log n. This is the same thing as if I would have sorted it, but it just looks cooler. Because it's O of n space for the numbers, we add all the numbers to it, and then we just grab the kth one from the top. Arguably, I think this is slower than having just sorted the list and iterated, because here finding the kth element is done in n log n time, while rather log, actually no, this is faster. No it's not, because this is done in log n, while if I just sorted the array itself, would have been done in O of 1. Yeah, so this is still too slow for it. It wants n log n, but I didn't, it wants n, but I did it in n log n. Yeah, not the quickest thing, but it works. So, I think honestly I'm probably just gonna call it here. I need to go have my breakfast. Edge cases. Okay, so I think that's gonna be it. It's another day. I mean, these are working solutions, not optimal for sure, but they're working. But yeah, that's gonna be it for me. Thanks everyone for stopping by. I will be back tomorrow, same time, hopefully 10, maybe 10:15 now, depending on what time I get back from the gym. But yeah, thanks everyone for stopping by, and I'll be back tomorrow.